Hi, I'm Sudarshan Krishnan, Associate Professor of Architecture at the University of Illinois at Urbana-Champaign. My presentation today is about the stability behavior of state columns. A state column typically consists of a central core with either made of wood or hollow steel tube, with cross arms attached at different elevations depending on the number of tiers of cross arms. The layout of the cross arms could be either cruciform as shown here, or they could be triform. That means the legs of the cross arm are at 120 degrees with respect to each other. Here's a detail of a steel cable stayed column, a hollow steel section as the core, with cross arms welded to the core and cable stays attached from the tip of the cross arms to the column ends. Some applications, this is the Astrup Fearnley Museum in Oslo, Norway. The structure uses an abundance of cable stayed columns. For a good reason, the architects wanted to showcase and reveal the nautical heritage of Norway through the structural expressionism of stayed columns. This is the Algarve Stadium in Portugal, which uses 4 cable stayed columns, 2 of which are seen in the picture. They are the tallest of cable stayed columns, 72 meters in height, and they support the fabric roof over the stands. And the engineers recognized that the use of cable stayed columns reduced the weight of the columns by up to 50% and also made the overall look of the column elegant as compared to using the tube alone. So when a cable stay is justified, if we equate the yield force to the buckling load of a column and calculate the slenderness ratio and knowing the radius of gyration, we can calculate the minimum length for which cable stayed column would be justified. We know that slender columns are vulnerable to buckling, and so are cable stayed columns. Now, analysis method and numerical methods for this solution for P critical is very important. And we use the stiffness probe method. This was developed at the University of Illinois by Professors Gerfinkel, Miller, and Robinson. The method uses the incontrovertible fact that the stiffness of a column degrades to a lower value as the applied load P is increased on a column, and it becomes 0 when P reaches P critical. But what happens is usually at the onset of buckling or close to buckling, the transverse displacements are very high in a column, almost meaningless, and that leads to certain inaccuracy in computation. So in order to make the method stable, what we do is we introduce a spring of a certain finite stiffness. So now this column is an augmented column whose stiffness is equal to the stiffness of the cable stayed column itself plus the stiffness of the spring. And then you apply the perturbation force to create the initial imperfection, after which you apply the axial load P, and then you calculate the stiffness and see the degradation of the stiffness as the load is increased. And this plot shows that. So as P increases, the stiffness of the augmented column decreases up to a certain minimum value, and that minimum value is equal to the value of the spring and at that time we know that the column has buckled because P will be equal to P critical. For more on this method, please read this paper. 3 columns were analyzed, and the results for 2 of which will be shown in this presentation: a single cross-arm column and a double tier cross-arm column. Now, 3 stages of loading must be understood for a pre-stressed column. One is when the column is pre-stressed. There's no applied load on the column yet. The second is a service condition when the column is pre-stressed and the applied load P also acts on the column. And finally, at failure, when P reaches P critical. But the important part here is to understand that P critical is not as important as N critical, which is the force in the tube. And that equals the value of P critical plus the residual tension components along the direction of P critical. This chart is important to know the various limit states and quantities that help us understand the enhancement in stiffness that is provided by using cable stays. One, this line over here, which is marked as N sub E, is the Euler buckling load for the tube. So we use cable stayed columns to go beyond the capacity of the tube. So that's why this is a good indicator. The second indicator is N sub Y. Second limit state is N sub Y, which is the yield strength of the tube. And then you see the plot for P critical here, which is for the cable state column. And the difference between N sub E and P critical, this dimension here, is the enhancement in strength that is provided by using pre-stress stays. Smaller values of pre-strain must be avoided because those columns would easily revert to a tube alone situation because the cables will slack very soon under the action of small loads. Okay, here are the analysis results for a single tier cross-arm column and two-tier cross-arm column. Points to note are that the plots are for the variation of buckling load P critical about the y-axis with pre-strain about the x-axis. The blue line shows you the Euler buckling load for the tube. The red line is the yield strength of the tube. So any enhancement in the buckling capacity of the column is measured from the blue line up to the plot, which is shown for the state columns. And there are three sets of plots, one with cable areas as 0.5 square inches, the second with cable area as 1 square inch, and the third one with cable area as 2 square inches. And what we recognize is that when you have cable areas of 0.5 inches, the eigenvector or the buckling mode is the single lobe mode throughout for any value of pre-strain. But with higher cable areas, you get the two lobe mode, which is the anti-symmetric mode of buckling, to be formed before the one lobe mode, which is the symmetric mode of buckling. But there, for some cases, you may have the one lobe mode forming before the two lobe mode, but both of them are possible. And that's why calculation of both the one lobe mode and the two lobe mode are important in pre-stressed columns, state columns actually. So in conclusion, tension stiffening is an elegant way to enhance the stiffness of a column. There is material efficiency, as we saw in the Algarve Stadium. There was optimization of up to 50% reduction in weight. These columns exhibit counterintuitive behavior because we cannot ascertain whether the one lobe mode or the two lobe mode would govern the value of buckling load. And more tiers of cross-arm need not lead to higher buckling strength, just like higher pre-strain does not mean higher buckling capacity. And lastly, the stiffness probe method leads to an accurate calculation of the critical load for cable state columns while ensuring numerical stability. So these are some of the references used, and this is my contact information. Thank you very much.